Good evening, ma'am.
Yeah, hello, Garvit. How are you?
We are live, please.
Good evening, everyone. Welcome to the iFocus online lecture number 528 of the module Optics and Refraction. Today is the lecture number 3 of the module. The topic for today is quantum optics. We'll discuss about transmission, absorption, scattering, laser, and fluorescence. This lecture will be taken up by Dr. Kanika Bhardwaj, ma'am. The moderator for today's class is Dr. Garvit Bhutani, sir. He has done his MBBS from Government Medical College Surat and MS in Ophthalmology from PGI Chandigarh. He has pursued fellowship in cornea anterior segment from LVPI Hyderabad. He has numerous qualifications, DNB, FICO, MRSCS, and FRCO. Previously, he has worked at Center for Sight and DDU Hospital, New Delhi. Sir has presented multiple papers, posters, and presentations at various national and international conferences. And also, he's a member of several ophthalmic organizations in India and Europe. We welcome you, sir.
Thank you.
The chairperson for today's class, Dr. Aditi Krishna Agarwal, ma'am. She has done her MBBS from KEM Hospital, Mumbai, MS from MGM Medical College, Indore. She has pursued her fellowship in cornea anterior segment from LVPI and has done training in glaucoma from Arvind Eye Hospital, Coimbatore. She is the founder and medical director at Krishna Netralaya and also a senior eye surgeon specializing in cataract, LASIK, and corneal transplant surgeries. Currently, ma'am is the secretary of Gurgaon Ophthalmologic Society. She is the member of AIOS, Cornea Society of India, DOS, Haryana Ophthalmic Society, and many more. She has delivered many faculty lectures and has been invited as a guest speaker and presented papers at several prestigious eye conferences. Ma'am has received multiple awards. One of those is the Best Paper Award at the DOS conference and winner of WS OPL video session at AIOC 2023. We welcome you, ma'am.
Thank you. Thank you for the kind introduction, Sylvine. Thank you.
The speaker for today's class, Dr. Kanika Bhardwaj, ma'am. She has done her MBBS from Salem, Tamil Nadu, DNB Ophthalmology from iCare Eye Hospital and Institute, Noida. She has done her fellowship in cataract and refractive surgery from Center for Sight, Eye Institute, New Delhi. Currently, she's the associate consultant at Center for Sight, New Delhi. She's involved in training DNB and PG students and also mentoring fellows. She has received multiple awards for Best Video, Best Paper, and Poster at AIOS, DOS, WS, and various other conferences. She's also received Young Researchers Award for her thesis. Ma'am has had multiple publications on cornea, cataract, and refractive procedures in various national and international journals. We welcome you, ma'am. Over to you, ma'am.
Thank you, Sylvie. So without further ado, I'll just share my screen. So a very good evening to everyone. And today we are discussing quantum optics. We'll be discussing on transmission, absorption, scattering, laser, and fluorescence. So first, introduction to quantum optics. In the previous sections, we have studied that light is basically treated like a waveform, but quantum optics is just the other end of the same. Here, it is the branch of physics that studies the quantized, that is the discrete nature of light or the particle nature of light. So it not only treats light as a wave, but also as a compact collection of particles called photons, which are energy particles. And the quantum optics explains this phenomena which cannot be explained by the classical optics. So even though light is a wave, but the wave is also composed of small energy packets called photons. And this wave and particle duality is what brings about the various features. So coming to photon and quantum optics. So photons are fundamental particles of light and all other forms of electromagnetic radiation. Essentially, it is a quantum or a discrete packet of energy. They are massless and chargeless particles, and they travel at the speed of light, and they exhibit both wave as well as particle duality. So coming to the concept of wave-particle duality, we knew that in the previous section, Dr. Navneet has taken a class on the wave nature of the light and explained phenomena like interference, diffraction, and polarization. Today, I'll be focusing on the particle nature of light, and we'll be talking about the phenomena such as transmission, absorption, scattering, laser, and fluorescence. So coming to the phenomena of absorption, reflection, and transmission of light. So as we've discussed, light consists of these small packets, which are generally considered energy packets. And these energy packets are called photons, which are very small particles without any mass or charge. Now, when light, it gets incident on any object, then it can be responsible for three types of main phenomena. Either the light can be transmitted, that is, transmission can happen, it can be reflected, or it can be absorbed. So these three phenomena are also a part of particle nature of light. They're very important, and they also lead to other more advanced and important phenomena like formation of color and visibility of objects and their color patterns. So first, coming to the transmission property of light. So when the light hits a transparent or a translucent material object, it is able to pass all the way through that object. This is called the transmission property of light, and it does not get reflected or absorbed in the process. For example, if the light is traveling through a glass, for example, in this image, if we see a white light that travels and through a transparent material, it is able to pass entirely. However, once the material is coated, that is, the material is converted to opaque, the light is not transmitted further and it gets reflected back. So this is what transmission means, which means that the light is able to travel from one end to the other end without changing or reflecting or getting absorbed into the material. So every material is having its own transmittance. That means how much light can pass through it. So based on that, it is the proportion of incident light that will emerge on the other side, and it will determine the transmittance of that object. For example, transparent materials like clear glass or clear water allow most or all of light to pass through. Therefore, we can clearly see objects on the other side. So these are completely transmitting the light. Whereas a frosted glass, here some light passes through it, but some scatters. So images appear blurred or diffused on the other side. So this has a lesser transmittance. Whereas opaque materials like wood or metal, they do not permit any light transmission at all, and all the light is either absorbed or reflected back. So the eye's ability to see also depends on how well light can pass through its different structures and even through the artificial devices. Now, what are the clinical applications of transmission? So as we know, intraocular lenses, better the intraocular lens transmission, better will be the outcome of the procedure or the surgery or the visual outcome. Let's say, for example, if a lens is clear, the clarity of vision will be very good. Whereas if there are glistenings on the lens, it will start to scatter light, and therefore the transmittance will reduce and clarity of vision will be affected. Similarly, we have various glass lenses with coatings. So the transmission property is carefully engineered in these specialized coatings to manage the amount and type of light which is entering or reaching the retina. For example, we have anti-glare lenses, blue filter lenses, and others which provide more comfort and protect against light-induced damage. So based on these, we can apply various coatings, and therefore we can change the transmittance of the glass lenses so that a particular type of ray is prevented or is allowed to reach the retina. Then we also have light responsive drug delivery, which means there are certain kind of drugs which can be activated with the help of transmission of light. Mostly it is taken, it has role in the tumor therapies. So what happens is drugs are loaded into biodegradable polymers along with light responsive substances, and they go and they settle in the area to be treated. And when we expose them to the light, because of the transmittance of the cornea and lens and the vitreous clearly, this light would trigger these drugs, and therefore they'll be released. So this is an advanced kind of therapy, and obviously it is under experimental research right now, but this is where the transmission property is utilized. then we all know very commonly all the refractive procedures, they rely on the predictable transmission of light through the ocular tissues such as cornea, and it can include both for diagnostic as well as surgical procedures. For example, in LASIK or in any photocoagulation, the tissue's transparency will directly affect the efficiency and safety of treatments. Here is the example of an excimer laser correction along with a flap creation. So you can see once the laser is fired, there is a hair follicle obstructing the view. Later on, when the surgeon tries to lift the flap, there is an area where the laser was not transmitted because the cornea in that area was not clear because it was blocked. There was no transmittance through the hair. Therefore, it can lead to complications. So this is just an example where we need a very clear tissue with full transmittance so that the laser can work efficiently. Now coming to the another property, which is absorption property of light. So what does absorption mean? It means that the process by which the light in the form of small energy particles or photons is taken up by a material, and instead of reverting it back, it is converted into energy. Most often, this is in the form of heat. It could be internal energy within the atoms, molecules, or even the particles of that material. The absorbed energy will manifest as a heat, or it will change the material's electronic state. So basically what happens is incident energy falls on an object and the energy is transferred to the photons or particles of the object. And when this energy is released by the photons in a slow state, then it is released in the form of heat. So when electrons, that is the photons, they transfer their energy to the electrons in the outer orbits, they absorb this energy, they become excited, and they leave their orbits to move to higher energy level, which are away from the nucleus. However, this state doesn't stay for long because electrons cannot stay outside of their original space, and they have to come back closer to the nucleus in their original state. Therefore, these excited electrons, when they fall back to their original energy level, very quickly, they release the packet of energy which was absorbed in the form of a photon again. So this is just a schematic video to explain all of this.
We note that when an atom absorbs energy from its environment, an electron will move
Nucleus.
from lower
This is the
energy
electron.
ground state to a higher energy level or excited state. Electrons have a tendency to drop from a higher energy level to a lower energy level. So once they are in an excited state, they will release their extra energy and drop to a ground state. The energy they release is in the form of a photon or light. That photon will have the same energy as the difference in the two energy levels in the atom, the excited state to the ground state. The energy of the photon also determines its color in the visible spectrum of light. For all light, the energy of the photon is inversely proportional to the wavelength or color of light. As the energy of the photon increases, the wavelength decreases or becomes shorter. This results in colors closer to the violet end of the spectrum. As the energy of the photon decreases, the wavelength increases. These are colors closer to the red end of the spectrum.
So this is how absorption works. And once the energy is absorbed and released, then a different form of wavelength is emitted. And the wavelength will depend on the amount of energy released. Different materials can absorb different wavelengths or frequencies of light depending on their atomic or molecular structure, and that will affect their color and transparency. For example, let's say a leaf. A leaf looks green because it is not absorbing the green part of the visible spectrum, but all others, and it is reflecting back the green. Therefore, we perceive the color as green. This process is fundamental to a variety of physical phenomena, which includes color perception, as I already told, photosynthesis, and even technologies like absorption spectroscopy. For example, we also use ophthalmic dyes. A lot of dyes are applied during eye examination. So these dyes, they absorb light and then they fluoresce to highlight structures like the cornea or retinal layers, which aids in clinical diagnosis. Now coming to scattering property of light. So scattering property of light actually refers to the phenomena where the light deviates from its original straight line path when it is interacting with particles or irregularities in a medium. Now, most importantly here, the irregularities play an important role. So if the light is traveling in a straight medium and it encounters any irregularities in its path, the light path changes and it starts to scatter. This interaction will cause the light to spread out, and this spread out light will be redirected in various directions rather than just passing or reflecting back in the same direction. So several factors influence the light scattering. For example, the particle size. So particles of the material and particles of the incident light, their sizing, if it is similar, then it can efficiently scatter light. The wavelength of the light, the shorter wavelengths such as blue and violet, they scatter more than the longer wavelengths like red. Therefore, this is why the sky appears blue. Then we have refractive index variation. If the media through which the light is passing have different refractive indices, then this can cause scattering of light because it alters the speed of light and it alters the direction gradually or irregularly. Then surface roughness. So smoother surface tend to reflect more, whereas irregular surface tend to scatter the light more. Now, what are the types of scattering? Commonly, we see various forms of scattering in our day-to-day life. For example, Rayleigh scattering. So Rayleigh scattering means the scattering of light by particles which are much smaller than the wavelength. This phenomena is responsible for the sky appearing blue. So what happens during the daytime, the blue light of the lower wavelength, it scatters easily in the atmosphere and therefore the sky starts to appear blue. Whereas during the sunlight, because the light has to during the sunset, the sunlight has to travel longer. So the longer wavelength red light scatters lesser and travels farther. Therefore, the sun and sky both appear red. Then there is my scattering. So my scattering means scattering by particles which are about the size of the wavelengths. This is what is responsible for the whiteness of the clouds. So because they are almost similar in particle size to the incident light, the white light is scattered in all directions and only some penetrates to the base. So this is why the clouds start to appear white. Then we have Tyndall effect. We've all studied in our school times in the chemistry labs. Tyndall effect is basically scattering of light by colloidal particles, usually seen in suspensions like in foggy air or when the milk is opaque or milky. So this is what Tyndall effect is. If you pass a light through a clear source, it transmits entirely. There is no scattering and the light travels in the singular direction. However, if there is colloid suspended in the solution, the light starts to scatter upon coming in contact with the particles which have similar wavelengths. So this causes a dispersion or a scattering of light, and this effect is called Tyndall effect. Now, what are the clinical applications of scattering? Firstly, in a lot of diagnostic tests, for example, the optical coherence tomography machine that we have, if we combine it with low coherence interferometry, then we can even measure retinal thickness and texture. This is a very advanced level of retinal imaging. Then we can use the property of scattering in grading cataracts. More is the severity of cataract, more is the scattering of light. For example, a person in whom the lens is clear, all the light is transmitted and focused to the retina. But when cataractous changes start to appear and the protein clumps are formed, then they start to behave like smaller particles and scatter light throughout the retina, leading to the blurring of vision. There are also dynamic light scattering instruments, which are also called as photon correlation spectroscopy. And these particles are used to measure the motion or diffusion of particles within the eye. And these are used to study experimental and clinical conditions of the lens, cornea, as well as the retinal vessels. Coming to laser. So laser is a short form for light amplification by stimulated emission of radiation. So what actually is a laser? It is basically a device that produces a highly focused, intense, and coherent beam of light by a process called stimulated emission. So laser takes advantage of the quantum properties of atoms that absorb and then they radiate particles of light called photons. But in a laser, all the light that is emitted is coherent and of a single wavelength. Instead of being in multiple wavelengths, it is a single wavelength light, and therefore it is very precise and highly coherent light. So a laser is created when electrons in the atoms in optical materials through which it is passing, such as a glass, crystal, or gas, they absorb the energy from an out source, such as an electrical current or light. Now, what happens? When these energy excites the electrons enough to move from a lower to higher energy level, they move to higher energy level and they again come back to their normal ground state. So once they come to their normal ground state spontaneously, then they transfer the energy to the next photon. Whereas when we continuously stimulate these electrons, then it is called a stimulated emission. So once they are stimulated, they emit even more amount of photons. So basically in laser, we are amplifying the stimulated emissions of these photons and electrons to form into a coherent radiation in the form of a laser beam. So what are the parts of a laser? So usually a laser will contain of three parts. First is the pump source or the source of energy. So this source provides energy in order to excite the laser medium. Now, once the laser medium is excited, it will cause population inversion. That is, more and more electrons will leave their orbits and go to the higher level orbits, and there will be an inversion of population in the outer and inner energy shells. So it can be in the form of an electrical source. It could be a flash or a light source. It could be any other laser such as a diode laser, or it could even be a chemical reaction. Whichever way we are delivering the energy, that is the pump source or the energy source. Then second part of the laser is the gain medium or the laser medium. So now the energy that is provided is thrown to the core material where actual light amplification will happen. So this core material can be a gas, it could be a solid, it could be a liquid, or even a semiconductor. Now, once this medium absorbs energy, then this starts emitting photons by stimulated emission when it is continuously excited by the pump source. The third part is an optical resonator. Now, these electrons, when they travel, they produce the emissions. So the optical resonance or the optical cavity is basically lined by two reflective mirrors, which amplify and they partially reflect light in such a way that a single beam is left out. So it is usually formed by two mirrors, out of which one is entirely reflective while the other is partially reflective. Then the cavity reflects the light back and forth and it amplifies it and then emits a coherent laser beam. So this is a simplified diagram. Pump source is the source of energy. Laser medium is any gain medium which will get excited upon getting exposed to the energy, and the emissions in the form of photons which are emitted, they will keep traveling between the optical resonator, which is two highly reflective mirrors, of which one is entirely reflective and one is partially reflective. So once all of these photons and energy particles are emitted and they cross each other and they kind of collide here and there, they are all amplified, and ultimately only a single wavelength beam is ejected out in the form of laser emission. So what is the working principle? Firstly, atoms will absorb the energy and electrons jump to higher energy levels. Then these electrons, when they are trying to return back, they randomly fall back to lower energy levels and they emit incoherent photons. Now these photons will then stimulate further electrons. This is called stimulated emission. So photon will interact with another excited atom and cause it to emit a second photon, which is identical in energy, phase, and direction. And this process causes amplification of the light. Ultimately, there is population inversion and amplification. So by maintaining more and more atoms in excited states than the ground state, we can continuously provide a stimulated emission, and the photons will continuously multiply, leading to the emission of a laser light. So what are the key features of a laser light? Firstly, it is monochromatic. That is, it emits only one color or wavelength. That is, a laser beam is of a single wavelength, and the color of the beam is again determined by its wavelength. It is coherent. That is, all light waveforms will have the same phase. That is, it is going to be, all are going to be in the same phase. So there is no interjection or cancellation. So they are all amplified. Then directional, so light travels in a tight, narrow beam and it doesn't scatter or diverge. And finally, high intensity. So energy is concentrated in a small area. So these four properties, the monochromatism, the coherence, the direction, and the high intensity are key features of any laser light. Now coming to lasers in ophthalmology. So we know that lasers are a very important part of therapeutics in ophthalmology. And these lasers are differentiated by different wavelengths and the mode of tissue interaction. For example, some lasers can be photocoagulative, some can be photodisruptive, some can be photoablative, and these are tailored to special tissues where they are targeted or the diseases which they are going to treat. So this is the tabular column explaining the various types of lasers that we use in our clinical practice in ophthalmology. For example, the argon laser. The argon laser has a wavelength of 488 to 514 nanometers, which is in the blue-green zone. And it is mainly used for retinal photocoagulation. It is also used in certain glaucoma procedures like trabeculoplasties. Then we have ND-YAG laser. So the ND-YAG laser is of the wavelength of the higher wavelength towards the infrared range. It is of the wavelength of 1064. And this we generally use for posterior capsulotomy or vitreolysis or iridotomy. The ND-YAG frequency double laser has half the wavelength of the normal ND-YAG laser, and this is mainly used for retinal treatments and even Pascal laser pattern therapy. Then there is krypton laser, though not very commonly used, but was previously used for CNVM treatment, and the wavelength is again in the range of 600 to 700. We have diode laser. Diode lasers are also commonly used. They are on the higher spectrum wavelengths. For example, the diode laser fall between 805 to 810, which is closer to the red range. And these lasers are used for ROP treatments or refractory glaucoma, where we do a cyclophotocoagulation using the diode laser, or even very deep retinal lesions. We have excimer laser. So excimer laser has a very short wavelength of 193 nanometers, and it generally falls in the UV spectrum. So excimer lasers are mostly used for corneal refractive surgery procedures like LASIK and PRK. We have femtosecond laser. So femtosecond laser again has a very short pulse duration, and its wavelength lies in the range of infrared rays. It is used commonly in refractive as well as cataract procedures. So let's go to the lasers one by one. So this is a simple depiction of where the various wavelengths and the lasers fall. So we can see excimer laser is closer to the UV spectrum with a 193 nanometer wavelength. Argon falls in the blue zone. Krypton falls in the green zone. Dye lasers or diode lasers, they fall in the infrared, and the ND-YAG and the carbon dioxide lasers are also towards the infrared. That is, they have more wavelength. So first, coming to the argon laser, like we discussed, it's a blue-green laser, and the wavelength is in the range of 480 to 500 nanometers. And this is mainly used for retinal photocoagulation. So generally, it could be an argon ion laser, or it could also be an ion gas laser, for example, argon fluoride. So what happens is, once the energy source or the pump source is applied, the particles in the argon gas, they get excited and they release electrons, and these electrons are then amplified through the optical resonance cavity, and emission is then taken in the form of laser reflection. So argon laser is absorbed by retinal pigment epithelium as well as hemoglobin, and therefore it is ideal for treating retinopathies and also sometimes retinal tears. It does have some risk like macular damage, so therefore it is not used very commonly close to the fovea. Coming to the ND-YAG laser. So Nd:YAG laser is with the wavelength of 1064, whereas frequency double Nd:YAG is 532. Most commonly in our clinical practice, we use Nd:YAG laser for posterior capsulotomies to clear out the posterior capsular opacification, or sometimes to break vitreous opacity like vitreolysis, and mostly for the peripheral iridotomy PIs that we make for shallow chambers in glaucoma treatment. The frequency double Nd:YAG laser is mostly employed for the posterior segment, and it is absorbed by hemoglobin as well as melanin, therefore used for retinal therapies like proliferative diabetic retinopathy and edema. And the modern versions like Pascal, they are very precise and quick multiple pattern shots delivering lasers. So an Nd:YAG laser is basically a solid state laser where neodymium, yttrium, aluminium, garnet, solid state crystal is there, and the pump source or the energy source here is a flash lamp. So once the flash lamp provides the energy, the atoms in the Nd:YAG crystal, they release electrons, and the energy is further taken out in the form of laser output. Then we have excimer laser. Excimer laser falls on the shorter wavelength category towards the UV spectrum. It is an ultraviolet ray. It emits light usually at the wavelength of 193, which is UVC spectrum. And this is produced by excited compounds. So excimer stands in short for excited dimer, such as argon fluoride laser. This laser works on the principle of photoablation. So here, removal of the tissue is very precise by breaking the molecular bonds. However, the additional surrounding area has no thermal damage. So it's very safe. It is also called cold laser sometimes. It is primarily used in corneal refractive surgeries like LASIK and PRK, which enables very precise ablation of corneal tissue in order to correct the refractive errors. This is the example. Excimer laser is so very precise distinct spots can be managed, and they do not have any surrounding area. Interestingly, excimer laser was first not devised for corneal procedures or eye procedures. It was used for thermal etching on microchips. Then we come to diode laser. So diode laser falls in the 800 to 850 nanometer category, which is towards the infrared segment. And diode lasers are made from semiconductor materials like gallium arsenide or gallium nitride. So what happens is here there are two anodes or two junctions. So one is the negative anode N type or the positive anode P type junction. So the semiconductor has two anodes, and the source or the pump source is electrical here most of the times. So once the electrical supply is activated, then these photons will go through emission hole, electron hole recombination. That is, the laser gets excited by electrical stimulation, and from here, from the positive and negative side, the electrons travel, collide, and they produce light directly from the electrical current. So this enables small size and very high electrical to optical efficiency. The laser is near infrared, and this is also absorbed by melanin with deep penetration, commonly used in retinopathy of prematurity, refractory glaucoma. It is more comfortable for patients due to lack of visible flashes. So the two electrodes are negative and positive, and the pump source here is electricity. Coming to femtosecond laser, a femtosecond laser is a type of laser which emits very short pulses of light, and the duration is in the range of femtosecond, which is 10 raised to the power minus 15 seconds. So femtosecond laser doesn't work on photocoagulation, it works on photo disruption. The basic technique is mode locking technique. What happens is multiple longitudinal laser modes phases are locked, which generates a train of ultra short pulses. These train of ultra short pulses in a certain direction leads to mechanical separation and therefore an incision formation. So a plasma is formed, and this expands, which leads to the mechanical separation of the tissue. This is mainly used in femto-assisted cataracts and LASIK flap creations, and also in other corneal tissue cutting procedures like intacts, where we can utilize. So femto offers very minimally invasive and highly precise incisions. This is also a important part of armamentarium in the current times. Now, a little bit about photodynamic therapy. Photodynamic therapy basically uses a laser or a light source to activate a photosensitizing drug. So it could also be a light source, but mostly we also use lasers for this purpose. So the photosensitizing drug selectively accumulates in the diseased tissue, which is going to be targeted. And it is mostly commonly used for conditions like abnormal blood vessels in the retina and choroid, like those seen in wet age-related macular degeneration, choroidal neovascular membranes, chronic CSCR, and some other ocular tumors. So what happens here? We inject a photosensitizing drug. Most commonly in ophthalmic use, we use verteporfin, which is injected into the bloodstream. It goes and collects in the abnormal vessels in the retina and choroid. And after about 15 minutes, a very low powered red laser light in the range of 600 to 700 nanometer wavelength is applied. At this particular wavelength, the laser will activate this photosensitive dye, which is verteporfin, and this dye will start producing reactive oxygen species, which will cause blocking of the abnormal vessels without damaging the normal retinal tissue. So even PDT has even lasers have role in PDT for various treatment of retinal disorders. Coming to the last property of the light, which is fluorescence. So fluorescence is basically a process where a substance will absorb light and or other electromagnetic radiation at one wavelength and then almost immediately re-emit the light at a longer wavelength, which is of lower energy. So it absorbs higher energy and immediately releases a lower energy. So this happens because the absorbed photons, they excite molecules to a higher energy state, and when these molecules return to the lower state, instead of emitting equal energy, they emit photons of diminished energy, and this is seen as a fluorescent light. Now, key features of fluorescence are that it occurs very quickly, and the emitted light is typically visible and of a different color than the absorbed light. For example, most commonly UV light is absorbed and light is emitted in the visible spectrum like blue or green. So this is a basic diagram of how fluorescence happens. Basically, from the ground state, the absorbed excitation light leads to electrons moving to the excited state, and when these travel back immediately to the lower level, they emit fluorescent light. This happens very quickly. Now, what are the clinical applications of fluorescence? We all know we identify a lot of diseases by fundus autofluorescence. So fundus autofluorescence basically it maps the natural fluorescence of a pigment called lipofuscin, which is located in the retinal pigment epithelium. So we do not need to inject any dyes here. The lipofuscin itself has some amount of fluorescence when light is thrown on it, and this is mapped in the form of a retinal imaging. And it can tell us these areas where the damage to the retinal structure is more, where there is more concentrated lipofuscin. So this is an example of a fundus autofluorescence picture. Then we also have fluorescein dye, which is an orange water-soluble dye widely used in ophthalmology, like everybody sees. So we put blue or the cobalt filter light onto the dye, but the dye reflects back a green range. So that is also fluorescence. It is because of the fluorescent properties that we are able to identify the various epithelial defects, like for example in dendrites or epithelial defects. We also use fluorescein dye in fundus fluorescein angiography. So here what we do, we inject the fluorescein dye into the bloodstream, and then once it reaches the retinal capillaries and the vessels, then we click pictures. For example, in the image shown here, this again is helpful in telling us various neovascular proliferations or damages happening to the retinal vessels. So this is all for today. Thank you for your patient listening, and I hope I was able to cover the topic.
Yes, Dr. Kanika, thank you so much. It was such a nice presentation, such insightful. And I think you made this physics heavy topic Really, really interesting. So I think this was a good presentation to bridge the gap, between physics and patient care. And you gave such nice clinical applications. So, a topic which seemed to be very boring turned out to be a very interesting topic. So I think really, really very good. You put nice effort. In fact, I was making some notes while you were presenting because all these things are quite forgotten, and it's so good to revise and to understand how it's actually applied in clinical practice. So I think the way you explained, you made us understand how light interacts with matter. So just reading out the points that I made while you were talking, that how it interacts, and then how it is relevant to basic diagnostics as well as therapeutics. You spoke about physics of transmission, scattering of light, and also advanced concepts like fluorescence, LASIK principles, laser, femto, everything. So I think really, really nice.
Thank you very
So
much.
I'm sure audience would be having a lot of questions for you. We have any questions?
Yes, ma'am, we have a question which says, how do the anti-reflective coatings in the IOLs, they improve transmission, and what quantum optical principles are involved in that?
Okay, so anti-reflective coatings are not a part of the IOL design. It is basically UV absorbing principle. So instead of reflecting the light back, the intraocular lenses are designed in such a way that the normal lens, how the normal crystalline lens also absorbs the UV spectrum light entering into the eye, the IOLs are also made to absorb that so that the person doesn't have any retinal damage. And secondly, the vision quality is also superior. Like there are certain lenses which are yellow tinted, but there is no such thing as anti-reflective intraocular lenses. The anti-reflective lenses are basically in the glasses. And those work by the principle of course, reducing the scatter of light which is falling on them. For example, any bright beam that is falling on the eyes, instead of getting dispersed and scattered in before entering and reaching the retina, the anti-glare protective coatings or the anti-reflective coatings will ensure that the light travels in a straight line without getting dispersed out. So that reduces the glare and the extra aberrant light that is entering the retina. I may be wrong, sir and ma'am, if you have any comments on that. I've never heard of an anti-reflective IOL.
No, I think you're absolutely right. Because there's something called as anti-reflective coating for the glasses. I think somebody's probably confused because you were showing in your slides both of them one after the other, probably.
Any other questions? We have Suvi.
One question which says, how does light scattering in the lens contribute to glare and reduce contrast sensitivity in cataract patients?
Okay. So all of us know our photoreceptors are concentrated in a particular format. The more light sensitive, color sensitive, contrast sensitive photoreceptors. So we know that rods are basically responsible for the contrast part of it. The color and the sharpness of vision is related to the cone part of it. And cones are located more in the foveal region. So when a person develops cataract, and also the scattering property of different cataracts is different. Like a nuclear sclerosis cataract will not scatter that much as compared to a cortical cataract or a posterior subcapsular cataract. So based on the location, the type, and the density of cataract, some light may pass through the lens to the retina and some may not. So this affects the contrast and also the clarity of vision, and therefore the entirety of the light that is reaching the retina will be filtered out, or it will be removed, and the crispness and the sharpness will not be there. So that's why the lens proteins in cataract, generally what happens is the lens proteins, they become denatured. Instead of being crystal clear, the crystallines, they lose their crystal clear feature and they become clumps of matured protein. So these small clumps, they start to behave as a rough surface within the lens through which when the light passes is not able to cross, and it changes its path. And this change of path leads to a more diffuse kind of light reaching the retina, and therefore reduce clarity, reduce contrast, and also some amount of color is also absorbed, so reduced color sharpness or the saturation, like we say.
Okay, ma'am. As of now, we don't have more questions, ma'am.
Ma'am, you would like to add something? Dr. Aditi, ma'am?
I think you've done it so beautifully and you've taught us so much. So I think very nice because, when it comes to the link, as I was talking about, all those things are such basics. But of course, with time, you forget everything. And it's very nice that you've brought it up so well. And I must say, you worked hard for the presentation. You know your concepts. So it's very nice. I think it was a very great talk. Kudos to you. Very good.
Arvid sir, would you like to add something to today's lecture that I have missed?
I think you have covered pretty much what's needed to be covered. There are certain experimental and further research oriented things that probably also come under the application of quantum physics or mechanics. There is a concept of quantum biology which is evolving and is being discussed amongst the researchers that basically talks. So now they are talking about the latest research in MIT said uh, that you can't have both features of light together. Either it behaves as wave or it behaves as particle. So you can't have the two together. I'm not sure what the impact of that would be in our understanding of the systems, but the quantum biology actually talks about coherence, tunneling, and entanglement. These are all the different mechanisms which are associated with quantum physics is being applied nowadays to explain how our energy systems or the transmission systems for olfaction, that's your smell capabilities, and your vision are actually happening in our body. Till date, we believed that all these quantum reaction physics, everything happens at sub-zero temperatures. But now we are actually talking it happening at molecular level in human body to explain different enzyme reactions, catalysis, photosynthesis. Everything is being explained these days by the quantum biology and the different concepts of coherence, tunneling, and entanglement for basically enzyme reactions. They say that the photoreceptors are very efficient because it works by exciting the electrons, and then the energy travels from one cell to another, which is basically surface hopping, which then eventually brings us to one of the latest research about AMD, where they're trying to use melanin to actually treat and reduce the lipofuscin excretion, which is essentially the cause for the AMD patients. So there's lots more happening, but that's all in the, I think, laboratories yet, hasn't come to the clinics yet, but very comprehensive review of the clinic bit of quantum mechanics by you. I really loved the presentation. Well done.
Thank you, sir. In fact, when I was researching for the topic, I also came across a study where they are using the interferometry patterns to determine the retinal thickness in Alzheimer patients. Like they are linking the thinning of the retina and the structural changes in the retina to diagnosis of Alzheimer's early on before the symptoms manifest. So very exciting things probably coming up
Yes.
horizon.
Exciting world ahead, just like we have now AI almost integrated into the ophthalmology. Next will be quantum biology. That's the future.
So we are looking forward to an exciting future ahead with a lot of development and inventions for it.
Yes.
So
Yes.
do we have any other questions?
No, ma'am.
Okay. Shall we call it a day, ma'am and sir?
Yes, I think, yeah,
Thank
we
you.
can do that.
Thank you so much, ma'am.
Thank you. Thank you. And a
Thank you,
great
ma'am.
Thank
session.
you.
Thank you.